So, as Mehmet said, shared memory is basically a very fast memory you have available on your GPU. You can think of it as a cache, L1, L2 cache. Actually, it's a shared cache inside a GPU. So, as Mehmet said, it depends on how memory intensive your algorithm is. If you really access memory a lot of times inside your algorithm, it makes sense to move things to shared memory. And this is exactly what we will do for our stencil operation. The speed up you might get from something like this, obviously, aside from your algorithm, it also depends on the way you access the data. Sometimes, so reading data inside a GPU you usually read data in larger chunks. So if, for example, you have a complicated stencil which accesses data far away or which does not access data which is contiguous, then you might have slow accesses. So you can reason about it if you know how it works and you can understand it. And it's also very important to test and check the performance at the end of the day. And in the next sessions, this is what we will do. We will add shared memory to our heat equation example and then do some timing tests on it. So as Mehmet said, maybe we should do this after lunch. Lunch is provided at 12:30. So then let's do it right now. Let's go. So finally, another thing that Mehmet mentioned over here is that we use static shared memory. The thing about this is it's fast, it's super useful, but you need to know the size of this memory at compile time. You need to tell the GPU already that, hey, I need to reserve this memory for my own use, and this needs to be done at compilation. You can't do this at runtime. So what this means for us is, so let's look at what the size of the memory should be and if we can actually find that out at compile time. So looking at this image, we look at our chunk 1,1 and we see that it has a small halo region, and this total region inside the pink boundary, including the central core, is what we need in our shared memory. So really, the size of the shared memory we need to allocate is the chunk size plus the size of the halos on either side. So the way we define it, this is 2 times the halo size. And all of this needs to be available at compile time. So for those of you who are not very familiar with C++, this means all of our variables need to be const expr, the variables that we use over here. So the chunk size, the halo size, these need to be constant expressions. So let's dive right into the code and make some changes. So we go to day 2, adding shared memory. We can look at our README. What do we need to do? So inside heat equation, we need to define first the size of the shared memory we use. We need to do this at compile time. And then somehow we need to pass this computation to the kernel. This is because the actual command to allocate the shared memory, this shared memory allocation happens inside the kernel, which if you think about it makes sense. I mean, it's the kernel which is going to use this shared memory, so it is there that you must declare and define it. After that, what we need to do is actually fill in this shared memory inside the kernel, and then later on use it in our 5-point stencil. So let's just go through this. Maybe we can start by defining the size of the shared memory in our CPP file. So let's see, where do we do this? we can do this over here. Just before we define our kernel, let's see. Shared memory size. Okay. What should our shared memory size be? Well, it is very simply going again to our diagram. It is this area inside the pink region. So this is the core of the chunk size, plus the halo size. So simply chunk size plus halo size plus halo size again, because of how we define the halo. Now, chunk size is not defined as of yet, so I'm going to move this a little lower. Okay, so this is the shared memory size in 2 dimensions, but I'm missing something right now. Okay, our chunk size is 16 by 16. This is fine. This is our shared memory size, but how are we eventually going to define the shared memory inside the kernel? I will take you back to what Mehmet showed. So over here, we're declaring the shared memory as a C-style array of doubles. So this is a 1D array. It's also possible to deal with 2D arrays, but for the purpose of demonstration in this workshop and to show you some other features of Alpaca, we decided to use a 1D array for the shared memory. So, okay, let's try to convert this to a 1D array. What do we have? So shared memory size is chunk size plus halo size. Very simply, what we need is the product of the x and y components. So shared mem size 1D is equal to shared mem size dot prod. This looks reasonable, except for the fact that we missed a small detail. So since we are allocating static shared memory, as I told you, all of this needs to be known already at compile time. So our variables need to be const expr. This is how you define things as compile time. So obviously for this, all of the things that we use above also need to be constant expressions. So for example, halo size here is a constant expression. So this is okay. This should work. Next up is, now that we have defined the shared memory size in 1 dimension, what we need to do is to pass this to our kernel. So to the stencil kernel. And how do you pass something at compile time? Can anyone help me out? Brian. By using template arguments, exactly. So let's go into our kernel and let's define a template argument and try to pass things at compile time. So here's my kernel. For those of you not familiar with it, this is how you define template arguments. So I have a 1D shared memory size. What's a reasonable data type for this? Maybe unsigned integer. and I will call the template just shared mem size 1D. And there we go. Very simply, I have passed in at compile time 1D size for the shared memory that I need. I will use this later to actually allocate the shared memory. But for now, let's go back to our heat equation example and pass it to the kernel at compile time. So how you do this is very simply pass in the shared memory size 1D. Obviously, you need to do it after it's defined. And this is how you would do it. Just a moment. This is all reasonably straightforward. Unfortunately, we noticed that while I was making this example, there are some compiler bugs, and while this would be very nice to do, it doesn't work quite as you would want it because the product operation is not done at compile time correctly. So this is okay. I will just now show you a workaround that will work correctly, and it is simply to use x size plus 2 multiplied by halo size multiplied by y size is 2 into halo size 0. This is just a slightly sad workaround that we need to do, but I hope it's easily understandable. We are simply doing the multiplication of the 2D shared memory size manually. So chunk size is defined as y size comma x size, and we add the halos around, and that's it. So yes. Sadly, that also does not work. It's yeah, it's unfortunate, also compiler dependent. Something that we have to look into, but just to be straightforward with you, this is how it is. Okay, so I have a 1D shared memory size, I pass it to the kernel. Very cool. Now let's go inside the kernel and actually define our shared memory. So we pass it in as a template argument, an unsigned integer. Let's see if it's actually an unsigned integer. I haven't said it. I will say it explicitly just to make sure I don't mess up my types. So inside the kernel, what do I do? Well, very simply, first of all, I create the shared memory, I allocate it. And to do it, as you can see over here, what you need to do is alpaca declare shared variable. And so I will simply copy it. Of course, you can find it in my favorite cheat sheet. And this is how you can define and allocate shared memory on the device. So as you can see here, you get a reference back, and this is some shared memory for your kernel. If you try to allocate too much shared memory, say you have large chunks and you need a lot of shared memory, and you ask for it, at compile time you will get errors saying, hey, I can't give you that much. So this is something you need to be careful about. You only have a limited amount of shared memory on your GPU. But for our example, this should not be a problem. Again, I would suggest trying to play around. I'm not 100% sure, but is the shared memory amount accessible by function attributes? Maybe. Anyway, this is the declaration of my shared memory. What's next? Well, since I have it, I need to fill my shared memory now. And how?
Please point to the ampersand again. This is really important.
So the comment in the room was, this is really important to note that this is really a reference.
Else you leave it, you will have a copy.
If you miss this and somehow define this, you will really take a copy of this, and that's not what you want. You want to really use the shared memory that was allocated for you and not copy.
Not a copy per thread.
Not a per thread copy. Yes. So again, to be very clear, this is memory which is shared between all threads inside a block. So when you fill it, you can fill in this memory in parallel using all of the threads inside a block. Sound familiar? Maybe, because just a couple of hands-ons ago, we were filling in all of the chunk inside a block. This is basically the same. We now just fill in the shared memory inside a block.
There's a question in the chat about the underscore counter stuff.
So over here, you can see a template argument called underscore counter. And this is, well, this counter is here to make sure that your shared memory, which is allocated, is unique. So you might have multiple kernels which are using shared memory, and you want to make sure that they all get different shared memory allocations and not the same. And for this, inside Rene is joining, inside the argument, you need to make sure somehow that they are
So
unique.
it's not for the uniqueness between kernel. It is for the uniqueness within a kernel. So you could, in principle, call a function where inside of the function shared memory is allocated. So static shared memory. And in that case, if you would add, you can always add the plain numbers like 0, 1, or an integer number. But if you add here a 0 instead of the counter, and then you call a function where again also shared memory with the same signature is created, and then this factory maybe assumes that this is a unique memory, then this is wrong, because if you have the same type, so in this case it is double T shared mem size 1D, and you have the same ID, then it will be only an alias. It will not be new memory. That's something implementation specific. It was coming from CUDA. We can't do anything against it. So if you would call twice this line with the same ID, you have the same memory really. It's only an alias. Therefore, use this pre-compiler macro counter to be really ensure that this is unique memory and a new instance of memory, that you not fill up the first instance of memory and think, oh, and I now work on the second shared memory, and then accidentally you overwrite your data. That's very easily possible. But in most use cases, you do not like to have an alias, so use counter, and then you are safe that you have really new memory.
Thank you. So just to be more explicit once more, if you do something like this, really this reference to sdata1 and sdata2 are pointing to the same memory. And this is probably not something you want to do. So this is why this precompiler macro counter ensures that you have unique IDs. I hope that answers it. So now that we have defined our memory, we now go to filling it in. So what we need to do is fill in the core, but also the halo regions on either side. Interesting. How do we do this? Well, first of all, maybe it's good to define the total size of my shared memory in 2 dimensions. Would be convenient to use. So I already have the chunk size and the halo size. So I will over here define shared mem size 2D. This is simply chunk size plus halo size plus halo size. Oops. So this is the size of my shared memory in 2 dimensions. I know this. What next? I have to fill it. Well, we already saw how to fill a chunk of a particular size in parallel on the GPU, and this is simply what we do over here. We went over a chunk, and for each thread, we filled in the elements it is responsible for. And this is what we will do again. Only this time we fill in our shared memory. So let me start it over here. Okay. Now I want to fill in my shared memory, so I put in my shared memory size over here. Next, I want to fill in, so what is the index, the local index of my current thread? I want to know this so that I can later on map it to the element I want to fill in. Again, local index is simply I, j. Very well. Okay, this is my local index, but what part of memory do I need to fill in with this thread? This is a good question, and let's refer to the figure again. Say you are in an arbitrary chunk. You are the thread responsible for I, j. So let's say somewhere here. You need to first find your local thread index, shift it by 1, 1 because you have this halo region, and then account for the offset from the origin. So this involves a few steps, and once again, to just be very clear, the first chunk, for example, chunk 0, 0, the shared memory for it will include the outer boundary and something like this. I'm not sure if we have an image. Over here, yes. So over here we can see what the shared memory load must look like. For chunk 0, 0, this includes our outer boundaries. For chunk 1, 1, it includes data which is actually belonging to other chunks. So let's try to fill it in. For any arbitrary thread I, j, what we need is to get the offset from the origin. So maybe we can consider this as the origin and these as the halo regions, and fill these in. If it's not clear, let's try to just write it down and see if we can get it. So my global index would be, so I already have my block start thread index defined, which is the grid block index times the chunk size. Okay. What if I write this? I'm sorry, what is missing? The halo is missing. Well, let's see. For thread 0, 0, what is this global index pointing to? For the block start thread index, it is only chunk size times the grid block index. Going back to our image, this means thread 0, 0 for 0, 0 is pointing to the top left element, which is actually something we do have to fill. Okay. So for the base case, it's fine. Let's try to do this for 1, 1. We have an offset of chunk size in both directions. So if there were a halo, we would be sitting over here, but since we do not add the halo, we're actually inside the correct block. So again, this is something you need to think carefully about. Offsets can be tricky at times, and it's best if you have to deal with them frequently. That means you're missing a convenient interface to do it. And I would recommend that you write these offsets in one place and then use an easier interface to make sure you don't make mistakes like this. It's very easy to do off by one error. So, okay, this is the global index I want to fill in to my memory. This should basically give me all I need, correct? I have my shared memory. I start filling it in. Okay, shared memory at local index. Yes, this is what I want to do. But remember, for the purposes of our example, we were using 1D shared memory. So what I will introduce to you now is a very simple convenience function that we have in Alpaca, which you can use to map 2D indices to a one-dimensional index. And guess what? It is called map index. So Alpaca map IDX. Oops. And this will map your index from the dimensions you have to the dimensions you want. The way you use it is, so I want to map it to one dimension. I say map index 1 and I pass in my local index. This is the 2D index. So what else would you need to map an index to one dimension? So over here, for example, I have a 2D index and I want to linearize it. What do I need? Say this is 5, 5. Brian.
The extent of the domain you're trying to linearize.
So the answer is the extent of the domain. Absolutely correct. So what I need is the size over here, and I multiply it by the number of rows, and I get it. So map index does exactly that for you. You given the local index, you given the extents. So the extent is simply the shared memory size. And this will return local index 1D. So there you have it. You are now filling in a 1D buffer of shared memory using, so what do we want to fill it in with? Well, simply the value of the current buffer. So just to go over what the shared memory is helping us do again, you copy in the values of the current buffer to shared memory so that when you read them later to fill in the next buffer, you can do it much more quickly. So this is what we do. We fill in the shared memory with current buffer, new current buffer at global index. And since we're using mdspan, I can just and this is how you can fill in shared memory in parallel using all of your threads. Any questions? We will wait for a moment for the people online. I am being told that we have lunch served. Yes.
Our block size currently is smaller than the shared memory size by 2 each dimension. So in the end, after we loop through everything, we only do threads per dimension that actually still copy where the rest is hiding. How would you tackle that?
So the question is, right now the shared memory size is only larger by than the number of threads in a block by a factor of by 2 elements in each direction, up, down, left, and right. So when you loop over, when you fill in most of it, there's only a small remainder left. And this means a lot of threads will go into the loop and then they will need to exit early because they don't have any work to do. And how should we tackle this? Well, the answer is you don't. This is how it is. Threads in a GPU are launched simultaneously, but if you have some blocks which are, so there's nothing you can do. You just need to eat these no ops and wait for the threads which have to do some work. But again, this is just a remainder loop and there is no other way, I think, which would be faster.
Should we synchronize the threads right after?
Yes, so the next question was if we need to synchronize the threads right after, and the answer is yes, it is essentially important to synchronize the threads. So if, for example, after filling it in, we don't synchronize the position, the work of the threads, it may be possible that the next kernel is already enqueued and you're using
No, not the next kernel.
sorry, the next part of the
stencil.
The stencil is already enqueued and
Not enqueued. The stencil is started to be executed
for some threads. So the point is that the stencil can be started to be executed by some of the threads since they're already done with this work. And they will try to read from shared memory. But it's possible that since some threads have to do additional work while others have no ops, some threads are still filling in the shared memory. So you might have a state which is incorrect. You might be seeing zeros or garbage, and some elements are still not filled. So it is essential to synchronize after you fill in your shared memory. This is a very good point. Thank you. And the way you do this is by saying alpaca sync block threads. And this is how you synchronize threads in the block. The final step would be to now use this shared memory to actually update and apply our stencil. And we will do this after lunch. Going back. Yes, question. So for the people online, we have a 1 hour lunch break. I would say let's meet again at 1:30, so 13:30 Central European time. So 1 hour and 5 minutes later, to be precise. So, all right, see you soon. Okay, and we are back. I hope everyone had a nice meal and is energized. We're about to come to the end of the alpaca session, and we will soon switch over to the next part of the workshop, which is learning how to use OpenPMD and playing around with that. Where we left our code was we were trying to use shared memory to speed up our compute. So we calculated the size of the shared memory we would need at compile time. We passed it to our kernel. Inside the kernel, we allocated the shared memory. Then we also filled in our shared memory like this. And we ensured that once the shared memory is filled, all the threads have actually finished filling it. And only once it is finished, we can then go ahead and use this shared memory to update our next buffer. So this is what we will do now. And it's very straightforward. All I need to change now is how we access the memory. Earlier, I was using the current buffer, which is stored in this lower global memory. And now we will use sdata. So let me just copy this. I hope everyone has their sessions open. So what I want to write is accessing the shared data at the index corresponding to the global index. Interesting. So how do we do this? Well, our shared memory data is shared between all the threads inside a block. And if you look at how we filled it, we filled the global index at the global index for the thread at what was the local index linearized to one dimension. So really, to access the next buffer, so access the current buffer at global index, what we need is to access the shared memory at its local index. Sorry if I'm saying index too frequently, but the whole idea is that shared memory is local to your block, and accessing memory is done in local coordinates. So let's try to do this. Simply accessing the shared data at global index means I only need the local index 1D. Okay, I don't have it. I do have the local index, which is, be careful, incremented with the halo size over here. So let's think about it. If I am inside thread 0,0, what do I really need to read from? Well, let's see. Thread 0,0 is over here. And this is inside the halo region. So this is not something that we need to use in our stencil. So we take the offset and move to this block, treat this as our center, and then carry on. The important thing to realize over here is that the number of threads you run, apologies, ignore my last sentence, it's fine. So we have our local index, which is the index of the thread. We shift it by the halo size. Currently, our work division is based on creating as many threads as our chunk size, or if there are more threads or less threads, just going over the whole chunk. So this is not going over the halo. Therefore, I need to move my local index by the halo size and then linearize it. So I can just copy and paste from what I did earlier, that my local index in one dimension is just mapping this local index and using the shared memory size in 1D. And that is pretty much how you will access uCurrent buffer at the global index. Any questions? This is slightly tricky. Again, it is very easy to commit off by one errors, to think you're in the right place, but actually have an offset. So I want to make sure that everyone is on the same page. So, okay, we have a 1D local index. This is how we access the central element. Now what we need to do is actually access the data on the left and the right. So this is what we had earlier, uCurrent buffer, and we were adding 1. So this is the right element. Okay. In our linearized array, what we can do simply, because of how it's linearized, we were just going through all the rows and storing the data. So to go one step to the right, all you need to do is add 1. Similarly, if you want to go to the left, all you need to do is subtract 1. Okay, fairly easy. The next step is, so this says the y index plus 1, so you are going down. Also, fairly straightforward. All you need to do is add, drum roll please, just the size of the number of columns in your chunk. Not quite true. So I said what you need to add is the number of columns in your chunk, but actually this is incorrect because the size of your shared memory also includes a halo region. And this halo region is really needed because of exactly this issue, that you want to try to access data which might be outside your chunk. To be extremely clear, again, the area in pink is outside the chunk you defined. It belongs to some other chunks. So this is why it is important. So when you need to jump to the next row, you need to go over not only the chunk size, but also the halos on both ends. So thankfully, we already have a very easy way to do this. We already defined what is the shared memory size in 2D. So I'm just going to use this directly. So I say, okay, take the local index and jump over the shared memory size in 2D in the dimension of 1. I hear ones from the audience. And this is confused. This is correct. Since this is the one in the fast moving direction, so this is the number of elements you have in X. And that's what you have to jump over. So this gives you the data below your current cell. And finally, you can go upwards by subtracting this. So notice that we are really jumping around directly. We are not concerned with, for example, how we were concerned with pitches with global memory. Shared memory is a contiguous chunk, so we are exploiting that fact and directly using it. And that is pretty much it. So really, we filled in our shared memory, we synchronized all our threads, and then once all the threads are done or back together again, they start the work on the next section of the code. Question?
Yes. Since you start indexing again with block thread index, then there's a local index with halo size. I was wondering whether your the first shared mem size in X direction is completely within the halo. I was now wondering whether you used it in the calculation or not.
So,
because you do the class halo size and then convert it. Okay.
things are okay.
Things are okay.
All right.
Would it be possible to use MD-SPAN?
So the question is, would it be possible to use MD-SPAN? Well, we are currently using a one-dimensional shared memory, but it's possible. It's possible.
So, but you need to write your MD-SPAN definition by hand, because we currently do not provide an abstraction which is easily casting your memory to an empty MD-SPAN. You need to define which order your MD-SPAN has. Is it color major or row major? And you need to integrate at some level in the MD-SPAN exactly this linearization calculation. But then you have the nice interfaces. So MD-SPAN is doing the same at some point in the
So
some nice abstractions in between, which makes everything more complex.
Yeah, this would be something that could be developed in the library. I mean, it can be easily reused into the
Yeah.
So again, the comment was that can we use MD-SPAN? The question was, can we use an MD-SPAN here? And the answer from the room was, yes, you can do it, but currently we don't provide an abstraction for this, and you will have to select properties of your MD-SPAN like row major or column major and other things yourself. But again, this is something, of course, that can be added to Alpaca, but also if you're writing a library or if this is something you use frequently, this is pain that you have to go through once, probably not very hard, and then you have this easy abstraction to access memory like that. Yes, first time.
Okay, well, I have this question. Maybe it's more about if it's a good practice or no. Can you please put 1 second the picture of the
Yes.
counts in the room? Like if we use these 5-point stencil, then the corners of the halo, even though they are in shared memory, we don't need them, right? Because for the calculation of the chunk in the corner, I am accessing like up, down, left, and right, but I'm not using the actual corner.
It's true.
But the thing is, since I'm moving like in this one-dimensional fashion, if I return then to calculate the point above, then I will have to take into account like this position of the right corner of the halo when I'm counting how many steps I have to take to the left in order to achieve to achieve the point above me. And I mean, what I'm saying here is it might be a little bit too overkill to restructure all this halo just to avoid saving the corners of it. So it's better to keep it like this, like even though we don't use this piece of memory, these 4 corners.
So the insight from the room is that one might be tempted to skip the corners because our stencil is not actually looking to the elements diagonally. So these 4 corners are never used in any computation. And you might want to save on memory, but then it was observed that, of course, this might be tempting to save memory, but it doesn't really help and only complicates things further. So, yeah, this is true.
Simple is better.
Simple is better.
Yeah. So you will always face then with some branching and so on. So you need then to take into account, okay, I am a corner, so I don't need to load my data. Maybe you change then the layout that you don't store the data to save this four entries. And this will increase the code complexity. You will have more errors in, and this is not worth. It is a really, really tiny portion of performance. And most likely this will be faster because it's easier.
Yes, in general, premature optimization is the root of all evil. So keep it simple.
Does it also make a difference with regards to essentially memory alignment? You essentially live with one as well? As you are, and your stuff isn't necessarily memory aligned for individual data.
For shared memory, the data must be always aligned to banks, and banks also need to build in GPU architectures. So, and in that case, it does not make sense, or not breaking any alignment if you skip one value also.
If it's 32-bit size.
Yeah,
In 64-bit, it still doesn't make it.
it's twice, so it's fine.
But if it's 8-bit, you get something.
There was another question, Mehmet, I think.
In order to use, instead of shared memory pointer, in order to use MD span, we just need to know the stride, which is pitch in units of data size. And if we give MD span the stride, then MD span, I think, can directly use. I'm trying it now. It's a good idea.
So there's already someone in the room trying to implement MD-span and use it for the shared memory. So sounds cool.
So when we were talking
Hmm?
of PIN already, because of all the index calculations, what is the advantage of using a one-dimensional array, or is there any advantage of using a one-dimensional array instead of a two-dimensional?
So no. In general, I don't think there is any particular advantage to use a 1D array for the shared memory, at least not in terms of performance you would expect.
Go on.
I mean, I personally chose it because I wanted to demonstrate map index and things like this, but there are additional comments which
Yeah, the one-dimensional indexing has also an advantage at the point where you fill up the memory. So, you fill up with two-dimensional stuff.
Yes.
No, then there's no advantage. There is more a disadvantage because you have this long address calculation. So it is in principle also possible to say at the point where you have the shared memory allocations that you like to have a 2D memory, and then you have the advantage that you save the address calculation, or the compiler can optimize on that level and knows a little bit more about it. 1D is very often quite easy if you have contiguous memory, because then you need only to have a for loop over it. Here we have a double for loop, handle really 2D, so there is no advantage for that, except that this allocation is easier, because if you have now here a 2D C array, you need to also take care about the indexing order, but it follows then the alpaca principles. The first bracket of the C array is the slow moving component, so it's the row, and the second is then the fast moving component. So so alpaca indexing is equal to C indexing in arrays.
I have a comment about double loop or single loop using. Since we are using double loop, it checks, and every for loop is also an if condition. Therefore, sometimes instead of using two loops, using one loop complicates the code but decreases the condition, because every additional for loop is a condition in that. Therefore, sometimes decreasing the dimension increases the performance. I observed this in some problems.
So the comment in the room was that to take advantage of the 1D memory, for example, we would probably need to reduce our two for loops and combine them into one, because each for loop is also checking a condition, doing an addition, and if you have two or more nested inside each other, then you're increasing operations. So if you want to really push it, you can combine these and go over stuff in one dimension.
Can you show the code alpaca leads again? Thank you. Voilà, distingue ignore capital D and vector excuse the capital D. In the for loop.
Line 81? No, 89. Thank you. Okay. So let's try to compile this. And fetch MDSpan. Some errors. So the shared memory size I passed in as a template, I called it something different. So I need to change the name over here. Thank you. Will be explicit. Okay. Still no viable overloaded operator.
Yeah, like it looks like the local ID is 1D, it has a size is of double of 324 instead of Type is strange.
Oh, interesting. Yes, it is strange.
Also, a short question.
So, okay, I found it, yeah.
Did you find shared memory size 2D somewhere?
Yes, at the top. So, okay, there is something I overlooked in particular. So, alpaca map index returns a alpaca vector, I think, or at least, yes. So, what we need to do is, since we are mapping to a 1D index, we know we will get a 1D index, so we access the 0th element. And this is what I need to do also over here. So when I'm mapping indexes, so for example, if I were to map this to some other dimension, say 3, by also using appropriate arguments, then I could have accessed index 0, 1, and 2. So this was an oversight. Now we can execute using shared memory. And the results are correct. All right. So now we are finally able to use shared memory to update our next data. Very nice. If there are any questions, we can take them now. So the final thing I will do after this, of course, first I want to say that you can find the solution of every exercise in the code for the next one. Also for the shared memory exercise, there's a folder called recap. After 7, adding shared memory, you can find the solution of shared memory addition over here. What I want to do now is just shortly look at how fast these things run. So obviously, we tried adding shared memory in the hope that it will bring us some optimization. But as I recommend always, it's important to measure things. So let's look at some timings. So I will go to the folder which holds the timings. It's called 8 timing inside day 2. It has 2 folders inside it, without shared memory and with shared memory. So let's start without shared memory. And let me do this. Interesting. Sorry about that. Maybe I should read the README. No. So I forgot to enable timing inside CMake. Sorry. Over here you can see enable timing. I will enable it. Make again. It's called enable timing. So on your CMake -d enable timing, or inside the CMake you can find it. Yes. So the purpose of having this enable timing flag is to disable non-essential work. So for example, all the waits with image generation and things like this. So these are automatically disabled in these timing branches when you set enable timing to true. So over here you can see that our simulation took 5.9 seconds almost, and this is without using shared memory. Let's try this out for the case where we do use shared memory. So again, enable timing, enable the HIP backend, and fetch MDSpan. So this is the runtime you will get when using shared memory. And it is slower. So this is an important learning point that you might think it's worthwhile to use something, it might not be. You need to measure it. It totally depends on your use case, the way your algorithm is written, the way you access your memory. All of these factors play a huge role in how fast your code can be and whether it is worthwhile to actually use shared memory. So in general, if there are objects that you know you will access again and again, it might be worthwhile. And this is something that can happen if you don't measure things and optimize without thinking.
But please mention that this benchmark is not suitable because the GPU is totally underutilized.
So the comment was that this example is absolutely not suitable to demonstrate the benefits of shared memory, and our GPU is completely underutilized. So, yes. I would recommend people to also play around with the sizes of the domain, make the chunk sizes larger, make the shared memory size larger maybe. So, and just try to play around. I'm sure people can find things where they break stuff, and it would be very useful, and you can gain some important insights just playing with this code. I highly recommend it. So, in general, this is all I wanted to cover in this initial workshop with Alpaca. We've seen how to write kernels, we've seen how to set up the Alpaca requirements, so devices, buffers, we've seen queues, we've also seen how to execute a kernel, synchronization, we've added shared memory, and at this point I think we've covered most of the important things that one would need to really start to write high performance code using Alpaca, which is completely portable and will run everywhere. We had a person in our group run Pick on GPU, which is built on top of Alpaca on a Steam Deck, for example. Just to tell you what is possible, it's write your code in Alpaca and run it everywhere. So now we have some time for questions, comments, and after that we will switch over to France and OpenPMD. Julian.
What was the particular use case to run Pick on GPU on a Steam Deck?
To show that it can be done. Yes?
Did someone else test it? Or
No, that is you.
Okay. Yeah, this is the answer. Because I bought the Steam Deck, I'm impressed about the technology. It's technology from the future, and I thought should be possible to also run Pick on GPU on it.
No, it's completely the wrong answer. You should have said that you want to program a game with real physics simulation in the background.
It's actually lasers and plasmas. How cool is this?
Yes.
I think part of the answer also comes down to programming the washing machine was hard, so
Yes. I wouldn't recommend it, but I guess you can try to run your code on a washing machine as well.
We don't need more English, that's hard to research.
Yes?
So this shared memory was slower.
Yes, so our example was actually slower with shared memory. Of course, this is not a normal situation. In most situations where it makes sense to use shared memory, you will get a speed up because it is a much faster memory. It's just the use case and the example we defined was this way.
You can increase the domain size and then the chunk size, and then maybe you would.
Do you measure with the timings only the hot loop, so the for loop,
That is
not the
correct.
initialization? Yes. So if you do also benchmarks, you need to take care your first kernel call or your first memory allocation. If you have a CUDA or AMD GPU device, will be slow because the vendor is then initializing the driver, is allocating additional context stuff and all this stuff. So you cannot measure really for performance the full application start and stop. So you could also write in front of your binary time, then you get also some timings. But this will also contain very fluctual stuff like initializing driver stuff, context creation, and. So therefore, he added really the timings around the for loop, that we only measure the hot code without initialization,
Yes.
most likely. And very often, if you think in terms of you program a simulation where you have repeating time step, in general, if you are on an HPC system, your initialization is most likely negligible compared to the real physics, which is ongoing per time step. So you very often compare only the hot loop, I say it always, because also from vendor to vendor, the initialization could be different. So we use, for example, in our Pickon GPU simulation, the random number generator from Alpaca. Under the hood, the API from the vendor is called, and the initializing the initial state for random numbers on one vendor is much slower than the other. But at the end, if you run your simulation or your application 12 hours or more, it do not matter if you took 1 second or 2 seconds in the beginning more at all. Yeah. One other benefit, maybe if there's no questions, if you use Alpaca in your application, we realized with Pickon GPU, where we was part of a testing system for Frontier, the fastest computer in the system. We got access very early to the system, before the system was assembled, to alpha hardware, you can say, and also to really broken software stacks and work together with the vendor to improve everything, to make it ready for the public, then that everyone can compute on the system. Then we was one of a few other teams, and we saw also the progress of other teams. And one thing what comes out is that it really helped that we use also in Pickon GPU, for example, Alpaca, because Pickon GPU is really the domain-specific code, even if we have on top of Alpaca also some a library PMake on top, which is then doing all the communication stuff and so on. But only having Alpaca as separate library and have the computing stuff, memory creation separated from the physics code, from the user domain code, was helping a lot in terms of finding bugs, try workarounds independent of your application. And it also showed, compared to other teams, those does not have this abstraction in between, that the porting from one vendor to another was much easier. So the typical way how you normally do a port to another vendor is that you have somewhere, maybe in the current, if you have a CUDA application, you have now inside of your application a lot of CUDA calls in. And then you go there and you swap all CUDA calls out and hope that everything is working. You can't test it independently. And it helps for our project, or it showed it's very beneficial if you have this separation, because you can very easily work with tiny debugging code to really analyze if it is really a problem on your side, or is it a problem on the vendor side, or in our case, if you use Alpaca, is it a problem in Alpaca side? Because there are so many possibilities where something could go wrong, and you need to separate this part. So an abstraction always helps. And in the last day also, Julian will say you something about best practices we learned from Alpaca, and he will maybe repeat 1 or 2 sentences of what I said. But yeah, stay and use Alpaca.
Yes. So I will check the Zoom chat.
It looks empty.
It looks empty. In that case, I will say thank you for attending the portion for Alpaca, and let's move on to OpenPMD. And I will invite Franz, and we will set up the session for a moment. So I will end the screen share now.